Okay, so this is kind of what we've building up to do. And that's this next reaction. This next reaction is named after a person that kind of first discovered this mechanism taking place. And it's our first really reaction that we're going to give a formal name to. So anytime you see a formal name given to a reaction, it probably means it's kind of important. And this is no exception. So, what we're getting ready to talk about here is something called the Dills Alder reaction. This is one of the more specialized reactions in organic. You know, the HBr and the addition of Cl2 and the addition of water and acid, those are not really what we call specialized. Those are what we would call general template forms of reactions. Dills Alder, though, is a little bit different because there's certain criteria that have to be met, and this criteria was discovered, and they decided to go ahead and name the reaction after the people that discovered this reaction taking forward. The reason that Dills Alder is so important, folks, is because this reaction creates new carbon-carbon bonds. So I'm going to put here very similar to chain elongation. So what that basically means is that I can take a compound with a certain number of carbons and take another compound with a certain number of carbons, and I can piece those two things together, and I can get a product that has more carbons than my starting reagents. Very similar to chain elongation when we started talking about the alkyne reactions, right? We said alkyne reactions we can elongate. How did we do that? Well, we amided it. We added sodium amide that ripped the hydrogen off a terminal alkyne that freed up a anion, and that anion served as a nucleophile that could go in and basically react with other things. Okay, so if that's the case with Dills Alder, this is another form of a chain elongation step, and those are very important when it concerns organic chemistry, because what you're going to see in Organic 1 or Organic 2, if you have to take it, is this concept that chain elongation is very rare. Well, there's actually a lot of reactions that elongate a chain, but what you'll see, they're very few and far between. So the Dills Alder reaction is going to go forward. It creates a product. That product has more carbons than what I started them out to be. But this is where it's a little different. It creates a cyclic molecule, a ring. Have we talked about forming rings before? I don't think so. If we have, somebody let me know, because I need to go back and watch those videos, but I don't think that we did. We've never really talked about making ring structures. How can we take straight chain molecules or branched molecules, and how can we form them together to give me rings? This is something quite new to us. Chain elongation, we're not impressed, but now you're talking cyclic structures. This is something brand new. It's a completely different territory than what we've been dabbling in the past. So, I think the easiest way to do with Dills Alder is just to look at an example of one. And before we do that, I want to show you Mr. Otto Paul Herman Dills. 1876, 1954, age of death, he was 78 years old. There's Mr. Dills, main chemist that contributed to the Dills Alder reaction, and Alder was the last name of the student that he had working in the laboratory on this project with him. He had two sons. Both of them were killed in World War II. 1950, he won the Nobel Prize in Chemistry, along with Alder for the Dills Alder reaction. And in 1945, 5 years before he was awarded the Nobel Prize, his lab and home was destroyed in a bombing raid. He finally decided, you know, folks, it's time to give it up. I see the signs. Whatever. I'll just pack it on up and I'll go off and I'll just mind my own business from this point on. His lab and his home was destroyed in bombing. His 2 sons were killed in World War II. Kind of tragic. But 1950, he did get the Nobel Prize on some of the research and some of the things that he was doing along with his student, and contributed to the world of organic chemistry. So let's talk about the requirements of Dills Alder before we do that example. Number 1, we need a conjugated diene. Is this surprising, folks? I don't think it is, because guess what? We've been talking about this entire lecture module. We've been discussing conjugated dienes. We've been talking about delocalization, single, double, single, right? This whole alternating conjugated delocalized system in a molecule. We at least need one. So number 1 requirement, conjugated diene. Number 2, we need another molecule. Takes 2 to tango, and it takes 2 for a reaction to take place. And this molecule either has to have a double bond or it has to have a triple bond. It has to be an alkane, or an alkyne. This has a special term. In this special term, do you remember electrophile? Loves little electrons. A nucleophile loves to be neutral. This is going to be called a dieneophile. What do you think that means? That's right. See, you thought I was crazy when I told you that kind of comparison to pedophile? Well, that kind of stuck with you, I hope. Because now a dienophile, you would look at that and say, it probably loves little dienes. And it does. So we have a conjugated diene that we need as ingredient number 1. We need another double bond or triple bond that we need as ingredient number 2. And we mush those 2 things together and we can form a ring. And we call that double bond or triple bond a dienophile for a reason. And we'll see that in our first kind of mechanism that we discuss. Number 3, we also need heat. Folks, to get these molecules to love one another, you often have to start with a hot tub. Kind of like real life too, isn't it, sometimes? And just like in real life, sometimes these molecules need a little bit of alcohol to get them to go forward too as a solvent. Who would have ever thought I could relate organic like that? But we do need a little bit of heat for this thing to go forward. So what this basically means is that I need to take my conjugated diene and I need to take my dienophile and I need to put it into a flask in a laboratory and I need to put some kind of heating mantle or some kind of hot plate up underneath it and I need to heat this solution up for a certain amount of time in order for this reaction to go forward. And what we form is a cyclic molecule. We form a ring throughout this process. And in addition to that, folks, this is a one-stepper. One step is all it takes. You know, very often we look at mechanisms and we say, well, this breaks and this adds on and then a carbocation's formed and then it could shift and then an incoming group can come on and take a look at that other carbon and that's where it decides to go and so forth. Here, though, it just kind of all happens at one time. I mean, they waste no time. No time. They come together in the hot tub, and then a few minutes later, bam! They've made a baby, and that baby is our product that we're going to be looking at as cyclic rings. Well, let's take a look at the general template. And this is what the textbook likes to show you. Again, I think this is kind of silly, because I don't think that it really conveys the message across to you. Conjugated diene to the left, a dienophile to the right. Those two things get mixed up and we put a little bit of heat on them and bing, we get a ring structure. How on earth? I mean, if you were reading this and you didn't have an explanation of it, would you be able to say that that was the product of this reaction? You probably couldn't. Well, what are some of the things that we can take away from this? Let's look at our conjugated diene. I have a carbon here, a carbon there, a carbon here, and a carbon there. And then this dienophile that they give me is another carbon and another carbon, and then this R group that kind of points off. Well, let's take a look at the ring. I've labeled 6 carbons, haven't I? 1, 2, 3, 4, 5, and 6. So maybe that's where the 6 carbons of that ring is coming from. 4 are coming from the conjugated diene, 2 are coming from the dienophile, and then we have this random R group that can also be part of the dienophile, and this random R group is still there, folks. It's still poking up over to the side. So maybe this is kind of setting up the template, the idea of how these two things are coming together. The conjugated diene are giving up, serving up some carbons for the ring, and the dienophile says, I'm going to bring what I have to the table too. Don't leave me out. And these two things come together and a ring structure is formed that we did not have before. And we have to talk about how that ring structure is forming. In addition to that, look at the double bonds here. We have a double bond to the left, a double bond to the right, and we have a double bond here. Well, in the final product, folks, we just have one of those double bonds that are left. So what's going on? Where are those other 2 bonds going? Are we breaking them? If so, how are they getting broken? Because it looks to me like we've only added conjugated diene and dienophile. We've not added any other reagent to break those double bonds. We've not added things like HBr or Cl2 or water and acid. We've not done any of that. Just these 2 ingredients sandwiched together, smushed, and they give me a ring. What does this even mean? This is the problem that people have with organic. So let's talk about it in common terms. And one of the first ways to understand the Dills Alder reaction and the Dills Alder mechanism is to set it up in the proper way. Okay, so what does that mean? Let's first start with our conjugated diene. All right, so the conjugated diene. To do this efficiently, take your conjugated diene that they give you in the problem and redraw it. Just redraw it on a sheet of paper. Again, you've bought the paper, you bought the pen, you bought the pencil. Use them. Don't let it go to waste. Hurts my feelings. So let's look at the conjugated diene, and whenever we have a conjugated diene, folks, I want you to write it like this. There is my double, single, double cause me trouble. So the double, single, double is standing up, straight up and down. And notice the way that I've pointed these double bonds. I've pointed them over to the right-hand side. This is a proper orientation for a Dills Alder reaction to go forward. So what I've done here is that I've given you a molecule, and this is it. Nothing else is on this molecule. That's all, folks. So this is a 1, 2, 3, 4. All right, so this is a butene, right? But there's 2 double bonds. So I'm going to have to change the ending here, and I'm going to have to say a butadiene. Diene, 2 double bonds. That happens at carbon number 1, carbon 2, and carbon 3. 1 and 3. 1, 3, butadiene. Now I need to bring in a dienophile. All right, so a dienophile is just basically a double bond. That's all that it is. Just a double bond. Okay, any double bond would work, or a triple bond would work too. It's got to have a set of pi electrons. That's the thing. So I'm going to keep it simple. And let's just use a carbon double bonded to a carbon. That's it. Nothing more. All right, so I've taken 1,3-butadiene, and I'm getting ready to add a 2-carbon eth and a double bond, ene. And I want to know what happens here. Okay, a reaction's going to go forward. I need a little bit of heat in order for this to go. Now let's take a look at this Dills Alder reaction. Number 1, a conjugated diene has to be in play. Check, ding, we've got that. It's to the left. Number 2, we have to have a dienophile. Well, we've got that too. Remember, it said a double or a triple bond. Check, ding, we have that. We have all the ingredients we need to make this cake. Or this organic product, baby. So here's the mechanism. I told you it happened all at once, right? So I'm going to give you the mechanism. I'm going to give you your first example of an Alder reaction right here and there. How do we do it? Folks, this is in the delocalization lecture. So that means that delocalization is going to take part in this decision-making process. Otherwise, they would have introduced it when we talked about double bonds. But they didn't for a reason. Delocalization. That's the driving force of Dills Alder. Because look at what can happen. Double, single, double cause you trouble because it's next door to another double. If these two molecules come in together, look at this. This could be double, single, double, and try to engulf that double as well into this system to improve the delocalization. We're almost tricking the molecule here. So this molecule says, hey, see that guy next door? I think we need to be his friend. I think we'll get along together. I think that not only would we get along together, I think we could get this guy to move on in. Share some of the responsibility. Share some of the electron love all the way around. That's what these two molecules are doing with each other. So this carbon says, psst, hey, you over there, why don't you come a little bit closer? And this molecule says, like hydrogen, okay. And this carbon decides to break that double bond right there. And it frees up a bond that would go here. So there's a connector step. Look at that. It's reached out, it's grabbed a hold of that carbon, and it's pulling it in a little bit closer. Well, when this happens, this poor little carbon was just ripped of a double bond. It was just ripped of some of electrons. So what have we done here? We've created a positive charge, just like when we predicted those other reactions back in the day. And depending on when you watch this video, maybe just a few minutes ago. Well, delocalization can happen here. That's a double that's next door to a cation. And delocalization can move. So this particular carbon says, oh, look at this. I've got a double bond, and next door there's a single cation. I'm going to go in for the kill. So, double bond breaks, and that double bond moves in. And when that happens, that carbocation takes care of itself. But in doing that, we just have another problem. And that problem is up here at this carbon. And that particular carbon now is shortchanged because that had a double bond, but it doesn't have one anymore. All right, so I'm going to rewrite this double bond a little bit better. I'm going to draw it a little bit straighter right there. And now this carbon has a hold of this one. It's pulling that molecule in a little bit closer. This molecule has now rearranged on itself. That's created a positive charge up here at this carbon. And folks, look at what happens. As this molecule gets closer and closer and closer in, what do you think is going to happen? Look, delocalization can take place again. We have a double bond, and that can be attracted to that positive. So this carbon says, hey, you, carbocation, you want some of my candy? Come on into the white van, hop in the back, we'll go away. And that's exactly what happens. Double bond breaks. That particular carbon flares out those electrons. And folks, a new bond has now been formed to take care of that positive charge up at the top. Well, that takes care of the carbocation. And look at what we have just formed. We have formed our cyclic structure. So what would be the product here? Well, let's redraw it. It looks like there's my starting carbon up here at the top. That now has a single bond to that one. That now has a double bond here off to the side. And now that has a bond that goes down in that direction. And that has reached out and grabbed a hold of this carbon that is a new carbon for the ring. And then that one has a carbon that was on it as well, came along for the ride. So that is that particular carbon. And this one reached out and grabbed a hold of the top. So we have taken a conjugated diene. We have reacted it with a dienophile. And we have formed a cyclic molecule. And almost every time, this will just simply be an alkene. It doesn't happen every time, but in a lot of the examples that we're going to be seeing, an alkene is still going to be left over, a double bond. That double bond is over on the left-hand side. We see that. We now talked about how that actually forms. So in this example, we've taken 1,3-butadiene. We have reacted with ethene in the presence of some heat, a jacuzzi tub. And what have we formed? You can name that. I don't have to coach you in how to name this. You can do it. This is a ring structure. We know that this is a cyclo. How many carbons? It's a hex. And there's only one double bond in there. So this is a cyclohexene. We've taken 1,3-butadiene, we've reacted it with ethene in this example, and we have made cyclohexene. Now, you might be saying, well, shouldn't there be a 1 in front of this? And the answer is, yeah, you can write that 1, but it's understood to be there. There's only one double bond. There's only one location that it can be in. So it's kind of redundant, but you can put it on there. I'm not going to yell and scream and take a fit. Folks, this is your first example of a Dills Alder. However, they do like to get tricky on you. And here's why. This is a very simplified version of a Dills Alder. So what these problems will like to do, what your standardized test would like to do, what Blackboard will like to do, what maybe one of my tests will like to do, is they like to try to trick you just to make it look confusing, but keep your template in the right orientation. This conjugated double bond, start off with those double bonds pointed in that direction, and then this double bond structure, draw it straight up and down. And that will set the template up so you can actually visually see the ring getting created very easily on a sheet of paper. If you do that, these problems become much easier. Here's why I'm saying that. Because on any one of these carbons, on any one of them, they can start putting groups onto these systems. And if they do that, it's going to be very difficult to keep track of if you are not careful. So that means that these products would also, or could also, have those groups on there as well. The problem, they're not going to get disturbed. They're not going to change. They're there. They're going to come along for the ride. No reaction is happening with those groups and those substituents. It's only between the conjugated system and the dienophile that a reaction is happening. And this is merging the two together to form a ring structure. Why am I saying that? Well, let's take a look at another example. What if they give you CH2, double bond, carbon, with a hydrogen, on a carbon with a hydrogen, double bonded to a CH2, and then they say, let's take that and let's react it with maybe CH2, double bond, CH, C, double bond, O, CH3. And they say predict it. What? What do they want me to do? They want me to take these two things and add them together and tell me what kind of product this form? Are they crazy? No, they're not. The reason is because you should know how to do this. We just talked about the template. We just showed you an example of a Dills Alder reaction. That same template gets applied here. Because, folks, we have a conjugated diene, don't we? That's the first one. Double, single, double, cause me trouble. And then over on the right-hand side, we have an alkene. I see the double bond. Notice it's the alkene that's reacting. I could care less about any other double bond in the molecule, so this C double bond O, that doesn't matter. Who cares about it? I don't. You shouldn't either. The conjugated diene reacts only with the alkene. That's it. Nothing more. All the other groups that are on there, it's coming along for the ride. We don't even pay attention to them. But this is where I'm telling you to set up the problem the proper way. Let's orient it in a way that makes it make sense. That's the only way that you're going to be able to predict these products a little bit better. So what that means, take this conjugated diene system. We have a carbon, double bond to a carbon, single bond to a carbon, double bond to a carbon. There we go. There's double, single, double. That's exactly what I have up here in a skeletal structure. I've taken these two double bonds and I've pointed them over to the right-hand side. I'm setting up my template. And then I know that the alkene part of this molecule is going to be important. All right, so I'll take the carbon and double bond to the carbon, and I'll write it straight up and down like this. So I can visually see this ring getting closer to forming. And it looks like off of one of these carbons, it doesn't really matter which one, I'm going to have a group that is a carbon double bond O with a CH3. I just pointed it down. You could point it up. You'll get the same answer. It doesn't matter. It's a very simple molecule. It's okay. Nothing over here on the left-hand side is going to make a difference. So there's only one way that we can form a product here. We get one type of product. That's it. So what type of product is formed? Take your diene and conjugate it. You have that piece. That double bond has now moved down. And you have this piece. There's the first part of the ring. Think of this bond opening up to grab over here. Think of that double bond opening up to grab there. And now we have the two carbons over here on the right-hand side. There's my cyclohexane ring again, right? And then down here on the bottom right, folks, that's still there. We haven't done anything to that. That's still a carbon double bond O with a CH3. Again, I just pointed it down. You can point it up. You can put it on the top carbon instead of the bottom carbon. It doesn't matter. It's the same structure. There's the product. But that is very hard to get to if you do not set these up in the proper way. So take the paper, take the pencil, write them down. Make them work the way you want them to work. You're the boss. You're in charge. You'll tell these molecules what they need to do. So put on the big pants and get ready to tell them how they need to line up and how they need to react. and then prove to me that you've got those big pants on by getting these answers right on an assignment. That's very hard to get to if you just deal with what they give you up here, right? That's way harder to see. So in the next video, we'll do a few more of these examples. We'll get used to taking these reagents, setting them up the proper way, reacting them together, and then forming products with them. And I think that you'll become more and more comfortable as we do more and more of them, right? Another thing I want to say before I stop this video, let's take a look at this group over here. This C double bond O, again, remember, is called a carbonyl. And if this C double bond O is between two carbons, and it is, there's one to the left and one to the right, then this entire setup is called the ketone functional group. We don't know how to name ketones. We don't really talk about that in the first semester of organic. We keep that until the second semester of organic. But getting familiar with the functional groups now will serve you much better in part 2 of organic if you have to take it. All right? Okay, so that's where this video is going to stop. In the next one, we'll pick up from here. We'll keep doing Dills Alder reactions. And I hope that you'll say, well, these aren't too bad as what I thought they were going to be. These are kind of fun. I hope that you say that at least. If not, just say it and lie to me. I would never know the difference.